In this video, I'm going to be talking about how we find the nth term of a linear sequence. Now, a linear sequence is a sequence that goes up by the same amount each time. So there are lots of types of sequences. We're only focusing today on linear sequences. And I want to make this very clear that the methods I'm going to talk about only work with linear sequences. So again, a linear sequence is a sequence that goes up by the same amount each time, or indeed down by the same amount each time. Here is an example of a linear sequence, or the nth term of a linear sequence. Now this form of writing is what we would also call a linear expression. So a linear expression is an expression where there are no extra powers of n, it's just an n term and then what we call a constant term. So we've got a number and then a letter plus some number. So this is a linear expression. You'll hopefully also have seen linear equations, which will be this equal to something else linear. This word linear keeps coming up, and it does just mean that there's no powers of n, that it is just n. So when we're talking about sequences, this is an example of a linear sequence. We have different names for the different parts of the expression. We call that first part the common difference, and we call it the common difference because this number here tells us what we're going up or down by. So I can tell quite quickly that this sequence is going down in fives because it's -5 as the coefficient. We call this coefficient of n. We also have a name for this red bit, this constant term, this thing without any algebra at all, it's just a number. We call that the zeroth term. And we call it the zeroth term because that is the number that you would get if you went backwards 1 from the start of the sequence. To show you what I mean by this, I'll give you an example. So here we have a sequence 5, 7, 9, 11. I can quite quickly see that this is going up in twos. So we've got 5 plus 2 is 7, 7 plus 2 is 9, 9 plus 2 is 11. So we're going up in twos. That tells me straight away that there's a 2n involved in my nth term. Oh no, if this isn't something I've made particularly clear yet, we call this the nth term because it's a rule involving n for the terms we're looking at. But we also sometimes call it the rule, we sometimes just call it the sequence. But anyway, this rule, this sequence, this nth term is going to involve 2n because we're going up in twos. So where's the zeroth term? The zeroth term is the term that would happen just before this 5. So if you imagine going backwards through the sequence, we're adding 2 each time. If you imagine that just before that 5, we would have had a 3. Now this 3 isn't in the sequence because our sequence started at 5, but if we use our imagination and went backwards, then we would have started at 3. So my entire nth term is 2n plus 3. So this is a method we can use to find the nth term, and this makes sense. And in fact, I can check that this works. So let's check that it works. When n is 1, I'm expecting to get 5, because 5 is the first term. So 2 times 1 is 2, plus 3 is 5. Lovely. When n is 2, I'm expecting to get 7. 2 times 2 is 4, plus 3 is 7. When n is 3, I'm expecting to get 9. 2 times 3 is 6, plus 3 is 9. And finally, when n is 4, I'm expecting to get 11. 2 times 4 is 8, plus 3 is 11. Good, so this is the rule that describes the sequence. Let's have a look at another example. So now we've got 5, 10, 15, 20. I can quite quickly see we're going up in 5 each time. So I know it's going to be 5n. I can then go backwards and find the zeroth term. So where would I have been just before that 5? I would have been at 0. So the nth term, so the zeroth term in this case is just 0. I don't actually need that 0 there. Doesn't do anything. So this sequence 5, 10, 15, 20 is just the sequence 5n, which makes sense because for every number we're timesing by 5. Here's another example: 5, 12, 19, 26. Now I can see that I'm going up in 7 each time to get from 5 to 12, we're adding 7 to get from 12 to 19, we're adding 7. So I'm adding 7 each time. So that tells me this is going to be 7n. The common difference is 7, so I'm going to have 7n in my nth term. The 0th term then is what I would have been just before I was 5, and that's negative 2. So the nth term is 7n minus 2. Notice how I've put minus 2 instead of plus negative 2 because they're the same thing. Be careful with your negatives, which is a very important lesson in most maths topics. Be careful with your negatives. Another example. Oh, here's an interesting one. This time we're going down in 7. So we started at 5, we went down 7 to get to negative 2, then we went down 7 to get to negative 9, then we went down 7 to get to negative 16. So this tells me that it's going to be negative 7n is going to be my coefficient of n. It's going to be my common difference. You might prefer to think of this as plus negative 7 because that's exactly the same as take away 7, but whichever way works for you. I then want to go backwards, so I think, well, where would I have been just before 5? What would my 0th term be? My 0th term would be 12, because then 12 minus 7 is 5. So here we've got negative 7n plus 12. Notice how this is a plus, because this is a positive 12. The fact that we were dealing with negatives before doesn't change the fact that this is a positive 12, so that's going to be plus 12. In this example, we've got 5, negative 15, negative 25. We are going down in 10 each time, so that's going to give me a negative 10n. If I look for the 0th term, that would have been 15, so we've got plus 15. One final example. 5, 3.5 to 0.5. Hopefully you can see we are going down in 1.5 each time. We're taking away 1.5 each time. So I'm going to have negative 1.5n. What would my 0th term be? My 0th term would have been 6.5. So we've got plus 6.5 here. Okay, so the key point from this video is that to find the nth term of a linear sequence, we first find the common difference, then we find the 0th term, and we can use that to build the nth term. So it's the common difference times n plus the 0th term.